It's 6.4.
6.4.
Yeah.
All right, I'm better. 6 points. I'll get a good mark. 6.47. What does it say?
A way specified by EI is equal to 12 pi.
EI equal what?
To 12 pi cosine of 2 pi times 10 to the 7 t minus beta 1 z plus pi over 4, all within AC.
Pi over 4?
I mean AX. Volts per meter is easy from a non-magnetic lossless. ER equals 9.
So this is ER equals 9?
Yes, sir.
Okay.
At Z less than 0, get a medium from Z greater than 0 with sigma.
Is it region 2's got the signal?
That's medium with, yeah, region 2 has a sigma greater than 0. Sigma is 0.02.
Okay.
And UR equals 2, and A to R equals 16.
So this is in region 2, those things?
Mm-hmm.
All right, this is in region 1, we've got epsilon relative to 9. Is mu relative 1 here?
Yes.
Yeah, that's the non-magnetic losses.
And this is sigma equals 0 in region 1, is that right?
Yes.
All right, what does it ask for?
Find HI.
This is normal incident, right?
Yeah, I think this one's normal.
All right,
Yes.
I've got to make this point. Now, we talked about oblique incidence last time. That means when it's coming in at an angle, here's the surface that divides region 1 and 2. So in region 1, if it was oblique, it would be coming in like this. Follow me? It's not. It's coming in normally incident, so it's in the z direction, all right? So we can say that the unit direction, a unit vector in the direction of propagation is just a z. Follow me, class, on that one? That's for the incident wave. Go ahead.
Find H of I, E of R, and H of R.
All right, so they want H of I. They want what?
E of R.
E reflected, all right.
Then H reflected.
H reflected, what?
E transmitted, and H
E
transmitted.
transmitted, this is getting better. And what else?
H transmitted.
H transmitted, all right, so they want everything. All right, I'm gonna cut to the chase on this one. Most of the time, they're worried about the magnitude, not the equation for the H field, understand? Or the E field. They just care about the magnitude. They know the direction of propagating. So all this other stuff in here is kind of a joke, all right, in a sense. Now, what I'm gonna do is go from this equation, the incident field, I'm gonna put it in phasor form, all right? But before I do, let's get one thing straight. The frequency of the wave never changes. Did you hear me? The frequency of the wave never changes. So right off the bat, grab the frequency and put it up here. What is the frequency? How do you get it? You look right there, and what is that? That's omega. It's the coefficient of t. Can everybody see that, class? All right, now omega is 2 pi f. If you're an electrical engineer and you don't know the relationship between omega and f, time to go back, take circuits again, because that is essential that you know it. Do you understand me, everyone? Omega is 2 pi f. So you just take omega and divide it by 2 pi to get f. When you divide that by 2 pi, what do you get? I hope you can read my writing. What? 10 to the 7th, or 10 megahertz. Right? I'm just going to put 10 to the 7th hertz for now. And here's the reason I do. My M's are lousy. They could be mega or milli or whatever. All right, I'm just going to leave it as 10 to the 7th. All right, now once you have that, after that, the next thing you get on these problems is the value of eta. Understand? Eta. So if we do this, I'm going to just put eta 1 up here. Eta 1 is equal to the square root of j omega. Matter of fact, I'll put omega down here. 2 pi times 10 to the 7th. And I'll just, the default units are radians, all right, per second. Default units of F are cycles per second, or hertz. Understand, class? So when we look at this, it's j omega mu relative mu naught in region 1 over sigma in region 1 plus j omega epsilon relative in region 1 epsilon naught. Does everybody understand it? That one you have to know. Got it? So now take your calculators. I hope you have them today. And go and punch that in. Try to figure out a way to do this efficiently. I mean, I know Mark Nelms told me this, Dr. Nelms, he's your department chair. He told me that a lot of times you can program your calculator, so you just enter the numbers and you've already got the formula stored in there. I don't know if you guys do this. Y'all know what I'm talking about? You can store a formula, you enter the numbers, and just bang. And I suggest you do that for things like this. So what? And that's 801. And by the way, I'm going to just put it over here. Do me a favor, give it to me in terms of magnitude and angle, if you don't mind, polar form. And then hold on. I know you're ahead of me on this one. This is going to be J omega mu relative 2, that's 1 actually, times mu naught over sigma 2 plus J omega epsilon relative to epsilon naught. Now the first one is kind of easy because sigma is 0. So I put it the full equation up there. So this one I just get rid of that sigma and I can get rid of the J omegas too. Can I, class? Y'all with me? So what do you get for that?
It's approximately 45.
Pardon me?
45.
40 pi? Okay. 40 pi. You can leave it in terms of just eta naught times something if you want. I do that so the eta naughts cancel usually, but we can put it as 40 pi. What is this one going to be? That's going to be complex, I think. That's eta 2, right? Is that right? What do you get for that one, guys? Magnitude and angle. That's 40 pi ohms, by the way. Do you have MATLAB on there, MATCAD or Octave? Right?
Do, yeah.
Well, it's so quick with those. I mean, you can just bang, it's done. The other ones, I tell you what I used to hate. When I was learning MATLAB, and you do it from the command line, that's slow. Now, if you do it from a script, it's fast, but command line, so. What do you get for this? Anybody got any two for me? Give me a magnitude and angle. Come on, guys, work with me on this one. I'm trying to get you. I was asking. This is a legitimate question. It's a good question.
That's it. It's 84.9
84.9 at what angle?
33 degrees.
32, did you say?
33.
33 degrees, okay. Now, we've got those two. Do you all hear me now? Now, the next thing we do that we're going to do is get the reflection and the transmission coefficient. Do y'all hear me? This is a normally incident wave. So the reflection coefficient is the ratio of the reflected field over the incident field's magnitude. It's a magnitude relationship, remember that. That's equal to, the reflection coefficient is going to be equal to eta 2 minus eta 1 over eta 2 plus eta 1. And I want to tell you one thing. A lot of times these complex numbers cause people to have problems with their calculators. So please, if you have a calculator, you're going to get a problem like this anyway today. So get them out and learn how to use them right now. If you don't know how to use your calculator, do it. Because see, the way I always put this in here, I put 84.9 e to the j and I put it in radians. All right? Now the value of this is going to be a complex number. It's going to have a real and imaginary part, but I always want it in terms of magnitude and angle. Can you all hear me on this one? So give that to me in terms of magnitude and angle. You have eta 1, eta 2. You could enter them in memory and just do the math on this one, all right? Say that again.
0.35 at an angle of 126 degrees.
0.35 at an angle of 126 degrees, did you say? That's 3.5. Anybody confirm that? I'm always just, you got that?
Yeah.
Anybody else? No?
That's fine, yeah.
Okay, that's fine, all right? Now you have the reflection, or you have the transmission coefficient. Now, you can, the reflection coefficient, you can also get the transmission coefficient. It's just 1 plus the reflection coefficient, or it's 2 eta 2 over eta 2 plus eta 1. Either one of these two forms is correct. Since you've got this already, just add 1 to it.
0.84 at angle 20.
Say that again.
0.84 at angle 20 degrees.
0.84
at angle 20 degrees.
0.84 at an angle of 20 degrees. All right. Now we have reflection transmission coefficient. Therefore, this transmission coefficient is the ratio of the transmitted to the incident field. You all follow me on this, class? Now, I can go ahead, and I'm going to tell you, if I wanted to take this equation and turn it into a phasor. I'm just going to do it here. Don't write this down, just listen to me. Right off the bat, I'd take 12 pi. That's the magnitude, right? Now when I put it in terms of phasors, this is the only thing I care about, these two terms. So it's going to be e to the minus j, and it's going to be beta 1. We can get beta 1 if we need it, times z, right? Then it's going to be that, and it's that will be minus pi over 4. The reason it's minus pi over 4, the way I want to group it, I want only one j term there. So if I group that angle, it's got a minus j beta z. There's the beta z, right? And then I pull the pi over 4 here. Now minus times minus is plus j pi over 4. Do you all see what I'm doing? Can you see it with far back people? I can't. All right, you good with that? Now it's in the AX direction, right? So that's phasor form of E incident. If I wanted the phasor form of H incident, I would just say H incident would be equal to 1 over eta 1. We have eta 1 up there, it's 40 pi. You all see it? Then it's going to be times the unit vector in the direction of propagation, which is AP, which is AZ. Follow me on this one, guys? Then it's crossed into this, EI. Now you'll notice that this is really just going to do one thing. It's going to change the orientation. When I go AZ, right, times AX, I get AY, don't I? So I get a change in orientation, and I get 12 pi over eta 1 over 40 pi, and this would be the actual argument. You all see that same argument as the E field. Now, I'm not going to go through all that stuff, because we can go through that all the way down. I care about the magnitude of the E field that's transmitted, E field that's reflected, and the H field that's transmitted, H field that's reflected. Understand? So now we're going to get them. Since we've got this information, we know the incident field's magnitude. I'll do it right here. So the incident field's magnitude is equal to 12 pi, right? That means the reflected field is the reflection coefficient, right, times the incident field. Reflection coefficient for the, where is it, is this. Now, see this angle? That would naturally be added on if you were going to do the problem, correct, class? I'm worried about the magnitude. Did you all hear me again? Magnitude. That means I only care about that. That's why I always want it in polar form. 0.35 times this incident field of 12 pi. Let me even be clear about this. This is what I'm after, because that's in the real world what you're after. So what do you get for this? Just take 0.135 times 12 pi, and what do you get? That I can't do.
13.194.
13.194, and that's volts per meter. Follow me? Now the transmitted field magnitude is just going to be the transmission coefficient times the incident field. And for that, the transmission coefficient is 0.84, so do that. 0.84% of 12 pi. I don't know what it is.
31.667
volts per meter, right? Agree? Now, if we want the H field, the only thing we need to get the magnitude of the H field is eta, right? The ratio of E to H is eta, correct, class? So now if I want the H field, incident H field, the only thing I do here is I take the incident E field and I divide it by eta 1. And just put magnitude there. That's how they do it in the real world. They don't care about phase. Not in these equations. Measurements are always done with magnitude. Well, take it back. Yeah, okay, there is something called coherency, but forget that for now. What do you get for this, guys? Just take 40 pi, is it right? Eta 1's 40. 40 pi divided into the incident E field, which is 12 pi. That's what? That's 12 over 40, right? And that would be amps per meter. Do you all agree with that? Forget the actual value. Are you with me, class? The pi's cancel, correct? Can you all, how many see what I'm doing here? I know I'm moving a little quick, but a lot of this is just kind of boring. Are you with me? Get H naught reflected, magnitude-wise. What is it going to be? It's E naught reflected, right, over eta 1. And what is that? Why don't you give me a number for that one? 12 over 40 is 6 over 20. Is 3 over 10 is 0.3, right? That first one's 0.3, isn't it, class? So this is really 0.3. What is this one? Anyone?
4 pi over 45, roughly.
I couldn't do it. 4 pi over 45?
4 pi over 40 pi, just as approximation.
1/10?
Yeah.
Anybody give me a real number? I mean, you're right. You're right. I'm not saying you're not right. I just want to give you exact.
0.105.
0.105? Thank you. 0.105. And finally, what's H transmitted? That's going to be E naught transmitted magnitude, right, over magnitude of A to 2. Make sure you use A to 2 in that one.
Keep it high.
Thank you. I'll get it up. Sorry about that. Don't be afraid to let me know. So this is going to be H naught transmitted is E naught transmitted over magnitude of A to 2, right? You got E naught transmitted there. You got A to 2 there. Do it magnitude-wise. Get rid of that angle.
0.373.
And that's amps per meter. Bless you.
Thank you.
Do you all agree with that, everyone? All right, I could put all that phase crap in there, but I mean, you're going to get it doing this. You understand? And it's straightforward to do it that way. Everybody got me on that, class? Now, again, when you get a complex angle down here where you get a magnitude or phase angle, then you got to take the phase angle up here. It means you change the sign when you put if you got 1 over e to the j theta, when it comes to the top, it's e to the minus j theta, then you just absorb it into the argument of the exponential. Got it, everyone? Any other question about that one? Did that's for power too or something?
Yeah, let's see. At a time, average power densities for the incident reflected.
All right, now, power. This is a good one. Listen. If it's lossless, you see how region 1 here is lossless, right? Sigma 0, correct, class? If it's lossless, the average power density in region 1, P-av will just be equal to 1/2 magnitude of the E. They want the reflected and incident power density?
Yeah.
All right, if it's lossless, it's always going to be 1/2 magnitude of the E field over the magnitude of eta. Now, if it's lossless, do you understand? If you got the incident E field, you replace that here, square it and divide it by eta 1. Got it? That's it. That's the incident power density. Matter of fact, I'll put incident and I'll put incident. If you want the reflected power density, P reflected, P-av reflected, then it's going to be 1/2 still magnitude of E naught reflected squared over eta 1. And the direction is going to be, if you want to be clear about this, minus AZ, because it's now reflecting. It's going the other way. Understand, everyone? The transmitted one's a little different, because for the transmitted field, you have an angle associated with eta, right? Now, the actual expression for power density, P-av, and this is going to be for transmitted, it's going to be 1/2, then it's going to be magnitude of the transmitted field squared over magnitude of eta 2. Got me on this one? Then there would be e to the minus 2 alpha z. If they wanted the formal, this would be an alpha in region 2, right? If they wanted the expression for all values of z, do y'all follow me? Because now the power density is going to decay because that's a lossy region, right? And just to be clear about this, sometimes I assume too much. In this region 2, gamma is equal to alpha plus j beta, right? And this is all 2. And gamma is equal to the square root of j omega mu2, right? Mu relative to mu naught, over sigma plus j omega epsilon relative to epsilon naught. With me on that, class? So now you're going to have a complex, you're going to have a real and imaginary part. I don't know if is that a good conductor right there? Is alpha and beta the same? I don't know.
Yes.
They are? Mm-hmm. So that means if that's true, the angle here is 45 degrees, right? And I can say the angle with eta is 45 degrees. Do y'all agree with that, class? And we actually calculated that, didn't we? Actually, we didn't get 45. We got 33. I'm sorry. So it's not a superconductor, but it's definitely a lossy region. Do y'all agree? That alpha and beta aren't going to be the same in this one. All right? Not if that's 33 degrees. But anyway, regardless of that, when I come to this, you can calculate alpha 2. Do you all agree with me there? We can punch the numbers and get alpha 2. How many see that? Make sure I'm not leaving somebody behind. You see that? But now you also have to put the cosine of the angle of transmit for the actual value of eta. And I'm just going to put theta eta 2 here. Now theta eta 2 is 33 degrees. Where is it? Where's it? Yeah, 33 degrees. Do you follow me on that, class? And that's how you would get the transmitted power density for all z, because it's going to decay. Did they ask for anything else? I don't think they can. We can get beta, can't we, in both of those regions, correct, class? And if I asked you phase velocity, that's always omega over beta, right? We've got omega, we can calculate beta for the regions, correct, class? You could get wavelength, right? Wavelength is 2 pi over beta, correct? I mean, we can go through every single thing we can get out of this, but I think we're milking it dry now. I mean, there's just so much. Y'all with me? Any other questions about, does anybody have any other questions about this before I raise? I'm not trying to go fast. Huh? I couldn't do it. No other questions? Can I erase this then? Okay. That's a good problem. Did Whitmore's book have, I mean, the solutions the same? Anybody?
The instructor solutions are.
Good. I think Stu did his own solution on it myself. He's pretty good. Any other questions before I move on? Any other questions about the homework? Y'all doing that homework? It just reinforces the actual concepts that I put forward. I mean that too. I'm not trying to stretch you on these things. They're just direct applications of what we cover in class. Now today what I'm going to do, first, let's see. We did oblique incidence last time, right? I was going through the formulas. I put the incident and incident E and H, the reflected E and H equation, the transmitted E and H equation, right? And then what I was about to do is get the transmission reflection coefficient. Are you with me on this, class? Now I'm going to just tell you this. I won't do it for this one, but basically when you're doing reflection and transmission equations, what you're doing is manipulating things based on one simple fact. At the boundary, at z equals 0, the tangent electric fields on one side of the boundary are equal to the tangent electric fields on the other, and the tangent H fields on one side of the boundary are equal to the tangent H fields on the other. That's it. Now from that, something interesting happens. It's called Snell's law. You had it in physics, but it talks about how things refract, or reflect really, through things. So basically, let me show you how the Snell's law is operational. And you should know this. What happens is this. If you have region 1 and region 2 here, I'm going to do something to make my life simple. I'm going to assume they're lossless. If they're lossy, it's slightly more complicated, but it's essentially the same thing. And what I'm going to do is say that here's the normal, that's the z direction. Call this the x-axis right here. And that's positive z. And I'm going to have, now with Snell's law, I'm going to do this for the TE mode. Transverse electric. So I'm going to have an electric field, an electric field coming out of the board this way. That's the incident field. It's going to strike here at some theta incident. Some of this is going to be reflected, and there'll be some, there's going to be a reflected field here, And then there's going to be a transmitted field. This is the angle of reflection, and this will be the angle of transmission. Now this is in your book. I'm not sure the page, and for this one, that's transmitted field. Now, coupled with this, I know I have a magnetic field, and I know that E cross H is the direction of propagation. This is the direction of propagation for the incoming wave. This is the direction of propagation for the outgoing wave. And this is the direction of propagation for the transmitted wave. You all follow me on this? Give me a page number of the book.
366.
366. If you want to flip through your books, go fine with me. I encourage people to bring their books. When I was in your shoes, taking classes, I would take my book and write in it. A lot of times, if the professor made comments, this is very important, circle it, do something, because you're going to lose your notes a lot of times. Or the dog will eat it. The book's usually going to stay with you. I mean, I got books from my physics, I think it's still my physics, I got my old electrical and engineering books, and this is going back really 50 years. It's a long time, yeah.
I meant 361.
361, correction. All right, now, this is again TE, transverse electric. It means the electric field is out of the board, right? You'll notice this, when it hits the region, the surface that bounces, it's parallel to that, isn't it? You all see that? The E field is transverse to the actual plane that the wave is propagating in, but it hits parallel to that. Now, usually I mention this. Usually what we do when we talk about regions with radar, we're talking about region 1 being air up here, region 2 being the ground. So when you look at this, perpendicular TE polarization, when they talk about that, they usually call that horizontal. Remember that. It's usually in radar and in a lot of applications called horizontal because the electric field is horizontal or parallel to the earth, right? When it hits tangent. The H field, on the other hand, you get by knowing that E cross H is the direction of propagation. I'm not going to do all this again, but you know, E cross H, direction of propagation. E, right there across the H field here is going to be in this direction, H reflected, and the H field here, E cross H, is going to be down like this. You can look in your book, he has it. You all see what I'm doing here? Just to give you a sense of things. Now, if we look at the equation just for the electric field for TE, so I can be clear about this, from last time we get this. We have E naught incident is equal to some, really, E incident is E naught incident times E to the minus J beta 1, and then it's going to be X times sine theta incident plus Z cosine theta incident, AY. The reflected field will be equal to E naught reflected, E to the minus J beta 1, X sine theta incident, but it'll be minus Z cosine theta incident because it's going in the opposite direction. We'll still have an AY sense to it. And E transmitted will be equal to E naught transmitted, E to the minus J beta 2 now, and then it's X, and it's going to be sine of theta transmitted minus or plus Z cosine of theta transmitted, AY. I want to tell you that I'm not smart, I just have to do this all the time, so I remember it. I mean, I have to write this crap down. I have to do this for every class, just about radar, EMC, I'm always writing this down. So that's the reason I know it. Yeah?
On your reflected equation, are those supposed to be beta incident or beta reflected?
This is beta 1, and this should be reflected. You're going to find out, sorry, and this is transmitted. You're absolutely, that's reflected. You're going to find out theta reflected is theta transmitted in about 1 second. All right, y'all with me on this? Now what we do is, to get Snell's, is simple. We say the tangent field in region 1 is equal to the tangent electric field in region 2. You'll notice that the electric field is the one that's tangent at the boundary, right? Y'all see that, everyone? Tangent means it's parallel to the boundary. Got it? Now, what I do for doing this part right here, I let Z equal 0. Now, when Z equals 0, that means right here, that's at the boundary. E tan 1 is E tan 2. Got me on that? That's Z equals 0. But it's anywhere with X. So when I do that, I'm going to go ahead and region 1, I have this waveform, E incident plus E reflected, that's in region 1, has to be equal to E transmitted. When Z equals 0, I got E naught incident right here times e to the minus j beta 1 x sine theta incident. Remember, z goes to 0, so it drops out. Got me? It is in the AY direction. I won't put that down. Then it's going to be plus E naught reflected e to the minus j beta 1 x times sine theta incident is equal to E naught transmitted e to the minus j beta 2 right here times the sine of theta transmitted. Again, just took the equations, take the incident plus the reflected, set it equal to the transmitted, let z equals 0 so the z cosine terms drop out. Got it? Now that's true anywhere. This is important what I'm about to cut. Yeah?
Should there be an x up there?
Yes, there should be. All right. Now, that's true at any value of x. Follow me? And the only way that's going to be true, listen to me carefully. I want you to think about it. Suppose I have something 30 e to the minus j, and I'm just going to put x right here, say, times a, plus 50 e to the minus j xb is equal to 80 e to the minus j xc. I'm doing this for a reason, all right? What you can gather is, if that's true for all x, it's surely true for x equals 0, right? At x equals 0, 30 plus 50 equals 80. Do we agree with that? It's also true for any value of x. The only way it can be true for any value of x is if these arguments are the same for all x. How many see that there? You all see that? They have to be the same argument. If ax was different than cx, then as I change the value of x, this would have a different value than this, and the phase would be different. You all see that? So this is the purpose, this is how Snell's law works. What they do is they say the only possible way this equation is true is if this plus this, these magnitudes equal that. Got me? Because it's true at x equals 0. Do you agree? At x equals 0, it's E incident plus E reflected is E transmitted. Bang. Now you got the magnitudes. Got me? But there's a second catch. It's true for all x, and it means this is equal to this is equal to this. Do you all see that there, class? Show of hands. How many see this? Now this is key to Snell's law. What it does is, in order for this, I'm not going to go ahead and write this. If for this to be equal to this, look, beta 1x, it means the sine of theta incident is the sine of theta reflected. It should have been an R there. You all see that? It means the angle of reflection is the angle of incidence. If anybody plays pool, you probably understand it basically means the angle that the ball bounces in it with respect to the normal is the angle the ball bounces out with, except if you put crazy English on it. But forget that. Y'all with me? How many play pool in here? I gotta make sure I'm talking to people that know what I'm talking about. Because half the time I'm not sure. I just get these looks, pool, what's that? I swim in it. I'm talking about billiards. I'm not kidding about this. I have people that don't know what I mean. All right. Now, the second thing is, so theta incident is equal to theta reflected. That's the first thing from Snell's law. Second thing is this, and this is important. Beta 1 x times sine of theta incident right here is equal to beta 2 x times sine of theta transmitted. You all see that right there? That's true. And if that's true, you'll notice what happens. The x can be taken out of there. Right? And that's Snell's law. Right there. That is Snell's law. Now, you can put it in any form you want. If you want the transmitted angle, can you all see what you could do is divide by beta 2, and I'd have beta 1 over beta 2, right? Times sine of theta incident right there would be sine of theta transmit. So if I took this, I took sine minus 1 of that, then I would get theta transmitted. You'll see that referred to as Snell's law too. It's just what? A rearrangement of the first one. Follow me? But this is the essential one, you remember. Beta 1, sine theta incident is equal to beta 2 times sine theta transmit. I got one more thing to say about this, and please listen to me carefully. If that is true, then for the lossless case, and I'll put it up here, then if sigma is equal to 0, alpha is equal to just j beta, and you could say that beta is simply equal to omega times square root of mu1 epsilon 1, or mu, just put it mu epsilon. Do y'all see that right there, class? Right? If it's lossless. Agreed? How many understand this? In the back. Y'all see it? Now if that's true, what do you see happening to this law? Well, then when I put beta 1 would be omega, right, times square root of mu1 epsilon 1 times the sine of theta incident would be equal to omega times square root of mu2, and I'm saying for lossless regions, this is lossless on both sides, would be omega 2 times epsilon 2 times the sine of theta transmitted. Do you all agree with that? What's the first thing you notice about that makes life easy? Look at omega. What happens to it? Poof, it's gone. That's right. It's gone. This is another form. So in a lossless regions where you have low loss or lossless regions, that becomes true. You all realize how you're going to have mu naught, mu relative, epsilon naught, epsilon relative. Over here you're going to have mu naught, mu relative, epsilon naught, epsilon relative, right? How many know that the mu naught, epsilon naughts cancel, right? How many see that? So you can further reduce this and say it's just equal to the square root of mu relative, epsilon relative in region 1 times the sine of theta incident is equal to the square root of mu relative, epsilon relative in region 2 times sine of theta transmitted in region 2. Got me on this, class? And furthermore, listen, furthermore, if it's non-magnetic, now I'm going to have to put it here, and this is important. I like to do a talk through if anybody's an archer and ever shot a fish or try to shoot something in the water. I can talk about some interesting things about this. Well, now when you take a look at this, if it's non-magnetic, then what I'm going to get is the square root of epsilon relative 1 times the sine of theta incident is equal to the square root of epsilon relative 2 times the sine of theta transmitted. Do you all see that? Class? Does anybody know what the square root of epsilon relative is usually referred to in optics? Why not? Why don't you know? The index of refraction. How many have heard that term? Anybody? Index of refraction. In optics, it's common. The symbol, the index of refraction, write this down. The symbol is just this n. It's not script, and I hate that symbol, by the way, because I can't differentiate my etas, which is square roots, right, of spreading mu over epsilon, right, for losses. N, the index of refraction, is just equal to the square root of epsilon relative in the region, which causes me some problems. I got to be real careful. That's index of refraction. It has values like 1, 1.5, 2, 2.5, small values. Not 8, 125, stuff like that. All right, now what it means is generally they put this equation for Snell's law is really N1, the index of refraction in region 1, times sine of theta incident is equal to N2 times the sine of theta transmit. Class, I'm supposed to give you a quiz today. I'm going to ask for a show of hands here. I would like to continue this lecture, but I'll stop and give it to you. How many are okay with a quiz Friday? If you want the quiz, I'll only give you one quiz on Friday. You won't get two this week, just this one, all right? Are you okay with that? Thank you very much, because I'm trying to get this down. You don't know what a pain it is to get revved up again and write all that crap down when you're trying to get this stuff out of the way. Are you with me? All right, now, yeah, breathe a sigh of relief. All right, but I'm going to give you one, and I'm going to give you the same one I got in there right now, so pay attention. Now, that's how you do it for optical problems. Got me? I have to do this now. We did TE. I'm going to put down the equations for TE. I got to say this. I do not expect you to memorize the reflection and transmission coefficient for oblique incidents. Understand that? I would always give them to you, the two involved, all right? I'll know them, I have to know them because I use them all the time. You don't, I'll give them to you. But you have to know for normal incidents. Got me? You've got to know the equations for normal incidents. Write that in stone because on Friday you're going to see questions related to that. I can't be more clear. All right, I've always been fair about what's on my quizzes, that's on my quiz. Done. Now, for my next trick, you guys ever have math professors that love to show off? Like, and for my next trick, I'll prove yours is flat. You know this stuff? I don't know what kind of props are in here with math, but I can tell you, I got some guys that, oh, they love to show off. All right, next up. Here's what I'm going to do. I'm going to just put down the reflection and transmission coefficients for oblique incidents. I put the fields down. Do you remember that? And I put E tan 1 as E tan 2, H tan 1, H tan 2. I didn't have time to go through the entire one. For TM, I'll do it. But I'm just going to put this. So this is going to be for the TE case, TE wave, between region 1 and region 2. I'm not going to write the equations again. All right, when you have a wave coming in like this at an angle, theta incident, we know from Snell's law we can get theta reflected, right? It's the same as theta incident, correct? We also know that this is the z direction and this is the x. We also know we can get this, theta transmitted from Snell's law. Do you all agree with that? Because really eta 1 sine of theta incident is eta 2 sine of theta transmitted. So we can get both if we have the incident, we can get the transmitted. We have the transmitted, we can get the incident, assuming we know eta. Got me on that, everyone? Now, what happens is for the TE wave, the ratio of the reflected to the incident field, and somebody make sure I don't make a mistake for the typo on this one, is equal, the symbol is just this, it's gamma TE. And the TE waveform is when the electric field is pointing out of the boards in the plane, perpendicular to the planes propagating. That's always equal to, and listen to the way I do this now. Don't write anything except put eta 2 here, because that's the region you're going into, eta 1 here, then eta 2 here, eta 1 here. Got me? Now, the coefficient of this will be the angle, cosine of the angle of the incident, not of the transmitted wave. The transmitted wave is in region 2. Follow me? So now we put cosine of theta incident here, then there's a minus sign, then it's cosine of theta, and this is going to be transmitted. This is theta incident, that's theta transmitted. Got me? So it's eta 2, eta 1, eta 2, eta 1, minus there, plus here. This is just going to carry this straight down. Cosine of theta, this is theta incident, pardon me. And this is eta 1 cosine of theta transmit. Now, if you look in the book, can somebody just amen. All right. That's it. That's bing, right? And that's a ratio of reflected to transmitted field, right? Then the transmission coefficient is the ratio of the transmitted field to the incident field. These are only the ratios of those magnitudes in front, all right? And that's equal to tau TE. And that's equal to 1 plus gamma T, thank God, right? Just add 1 to the top one, you got transmission, right? It's also equal to, just for completeness, it's equal to 2, and you check me on this, 2 times eta 2 cosine of theta incident over eta 2 cosine of theta incident plus eta 1 cosine of theta transmitted.
You have the
sorry. Cosine eta 2.
No. Yeah, you're.
I think I'm good. I just wrote them different.
Yeah, you wrote it backwards.
He has this one up front.
Yeah.
It's the same thing. All right. Now I just want to tell you, you don't have to memorize that. This is easy to work with in the first place. Just add 1 to the top one. You're going to need reflection and transmission almost always. Got me on this, class? That's all you need to know about reflection and transmission for the TE wave. One other thing in Dr. Wentworth's book, he makes this point, it's a good point. He says, when we talk about the power associated with the wave, you'll notice the direction of power flow is this way, correct? The direction of reflected power flow is that way, and transmitted power flow is this way. Now here's the key thing. When you talk about power flow, suppose I get the incident power density here. It would be 1/2 the magnitude of the incident electric field squared, right? And then it would be divided by eta in region 1, correct? But the thing is, you don't take this as the value that's true. You take the value of power that's normally incident. So you have to multiply that by the cosine of the angle. And the reason is this. Power flowing this way is always going to be the same. When you have power flowing that way, and then it's bent at this angle, they'll be different. Got me? It's always the normally incident power. So the power going this way would be the power density 1/2 eta 1, or 1/2 magnitude of the incident electric field squared, if it's lossless, right? Divided by eta 1, and then times the cosine of theta. I'll write this down in a second. You all follow me? That would be equal to 1/2 magnitude of the transmitted electric field squared divided by eta 2 times the cosine of this angle, all right? That formula's in the book. Can you give me a number for it? It's the conservation. 6.137. 6.137?
That's the equation, page 364.
On page 364. That's for power conservation, but I want you to make sure you understand the concept. Power flow in this direction, normal to the boundary, is a constant. Not on this, at this angle, all right, because the waveform bends. You follow me on that, class? That's the reason you always have to do normal into the boundary. Got me on this? People make that mistake. All right. Normal into the boundary. I could write the equation, it's there, but I just might as well do this for complete. You don't need to write it down. You start out by saying 1/2, and then you put the magnitude of E naught incident squared over eta 1. Now I'm assuming lossless. Then it's going to be cosine of theta incident minus 1/2 magnitude of E naught reflected squared over eta 1. Cosine, they're the same, cosine of theta incident is equal to 1/2 here, and it's going to be magnitude of E naught transmitted squared over eta 2 times cosine of theta transmitted. He has that, but he'll put in, here he'll put the reflection coefficient times E naught incident here, and he'll put the transmission coefficient times E naught incident. Huh?
That's exactly what he has.
Oh, that stinks. Because usually you cancel out E naught incident, and you just put reflection and transmission coefficients. But y'all follow me in this one, class? And it's the same for TM. Now I'm going to get to TM. That's about where I'm not going to get, because it's 10:50, 12:50. All right, I'm going to take care, read TM. I'm going to go through that one fast on Friday, and you are going to get your quiz. I'm trying to do a good job on this, because this stuff's important, and you really get it down for the next couple of chapters. This is crazy stuff.